relevance to tonight's talk. Tonight's talk is about efficient rebar splicing technology in concrete structures. Our speaker is Alessandro Rumi. He's Business Development Manager at BARTEC GROUP. He's got over 20 years of international experience, and he can be considered as a real splicing systems specialist. So I'll hand you over now to Alessandro to start the talk. Thank you.
Thank you, Declan, and good afternoon, everyone. And thank you for joining this webinar, where we would like to introduce this original project that we are developing as in BARTEC Group. The project is called STARS. Splicing technology allows reduction of steel. So during this presentation, which is more or less divided in two parts, we will try first to give the state of the art of splicing technology as per today, and the second part is more dedicated to this reduction of steel that can be achieved by specifying, by using splicing systems. This is it is important to say this is today we're talking more about a technology. We're not talking about a product, but more about this splicing technology. And the reason why we do it is we are splicing manufacturers, and we know that in the there is some, don't want to say confusion, but it's not completely clear because of lack of literature on the splicing systems, what can be the advantages and how these systems work. This is what we see very much in the market when they call us to explain it. This is more about the technology, the splicing technology, and I hope that after this presentation you this will help you to understand more the splicing technology as well. So first, let's see. It doesn't look, it's changing the slide. Sorry, but there is a little. Yeah, I hope this is now working. So first of all, a couple of words of who we are. BARTEC company is the inventor of the parallel threaded splicing system that has been called BARTEC. So a lot of there is this system, the parallel system is mostly known as the BARTEC system, comes from our original patent that came about 35 years ago. Linxion is the brand that we are using today to clear of any confusion, because all the BARTEC systems came up, and also fake BARTEC system. So we just to change, meaning the original company who created this cup, what they're manufacturing is called Linxion. So Linxion Dubai is a branch of BARTEC Group and is manufacturer of splicing solutions. So this is who we are. We have long experience. Personally, it's more than 20 years that I'm working in the splicing technology in this company, other companies as well. So I wanted also to share at the beginning some more information about splicing solution, the existing ones, and we will see in a minute what we are talking. What is STARS? STARS project comes from the fact that we noticed that when we talk about green building, most of the activity that we see in general today is to try to assess the carbon footprint of the actual product used. We try to do one different approach. We try to see how a product, how a solution, a technical solution can be related to the carbon footprint saving. And it's not about evaluating the splicing system itself, what is the carbon footprint of it, but more putting in relation with the traditional system for connecting the reinforcing bars. So this is what the project is about. And we're trying to show that by using mechanical splices, this can bring a consistent reduction of carbon footprint. So I will skip this part because it's more about reinforcing bars, and I believe that everyone is very familiar with reinforcing bars, what they use in the concrete structures. What is important is to know that ideally we would all want to have in a concrete structure reinforcing bars without any connection, to have a continuity in the structure inside, or we want to just interrupt the structure where we want. This is not always possible, because obviously the rebars can be manufactured in a certain length. They must be transported, and they must be cut and bent. So there may be a solution just to reconnect the reinforcing bars once they come to the job site. So the traditional way to connect the reinforcing bar in the concrete structure is overlap, meaning to join the two bars together over a certain length for correct embedment in the concrete. Welding, which is the least used solution today, is because it has a lot of issues for controlling, testing, and also installing, because you need a specific workmanship to weld properly the bars. And the third possible way of connecting reinforcing bars is through mechanical splices. So now, as we saw as we are seeing as couple manufacturers, that mechanical splices are more and more requested, because structures are changing, more adventurous, more futuristic structures are coming, and the more the element change, the more is needed to find solutions to sometimes to avoid to have the overlap of rebars. So, and this project started in Dubai because of this trend, because mechanical splices are very much used and very much popular in Dubai because of the type of the structures that are made in Dubai. Also, besides, we must say that the norms norms for ruling mechanical splices are existing, not everywhere, but there are a few reference norms that are used worldwide. The most used are the American norms ACI 318 and the British norm, and there is an ISO norm as well that was developed a few years ago. But we can say, if we talk about UAE, that the most used norms are ACI and BS. So what is a mechanical splicing system? It's very simple. It's a device to join two reinforcing bars, and with the aim of transferring the full tension or compression from one bar to the next. The most popular is we are the inventors actually of the most popular splice that is used today, is the parallel threaded system. Why is it that? Because it's probably the most economic as well. and it's the one that is that can respond to the need of the different applications that may be in the structure. However, there are so many systems available in the market that can be divided into two big families. One family where you need to do something on the edge of the reinforcing bar to connect it through a sleeve, so threaded couplers, or there are systems where you need to upset the edges of the bar with special couplers in between. And the second big family is a family where you don't need to prepare the bar before, but you need to, the coupler comes with a sort of system or a sort of way to be connected to the bar. So you can find maybe a swaged coupler where the coupler is fixed directly to the bar just by pressing it. There are couplers with grout, completely with grouts on both sides. This is like Japanese systems, for example, where it's a big sleeve with a certain embedding distance to be filled after with cement grout. Or there are other systems they developed a few years ago. Developed threaded. They made the ribs of the bar like threading, and the coupler to connect the rebars through the ribs of the rebar. Both couplers, there are so many different couplers, but we can say that 99% of the existing used couplers in the market are in the one of the first family, which with the thread can be parallel thread or other types of thread, conic thread, or applications. Couplers are designed also to be used in different applications. So, for example, the most simple problem that one could have is that it's not possible to turn the bar. When the second bar cannot turn, there might be a coupler or a system for allowing the connection of the bar through this metal sleeve in between. There are other applications that might be needed. So, like for welding a coupler to a steel structure, anchors to use a coupler instead of the bent bar, or transition from one diameter to the other. We can say that in the 50 and more years of history of mechanical splices, there are a lot of all the applications have been covered with special solutions with splicing systems. Typical projects. So couplers, as I said, 50 years of history. It's not a new thing. It's a very widely used system, very widely used solution. But we have to say that most of the projects where they are used are limited to the big concrete structures. So we think about nuclear power stations, for example, where a lot of couplers are used. High-rise buildings, stadiums, big bridges. Why is that? Is because it's all those projects where a larger size reinforcing bars are used. So we can say that the more the reinforcing bars are big in their size, the more probability that mechanical couplers are used, because the length of the overlap is long in those cases, and it's much easier to connect the reinforcing bar on site without having to overlap them, but so use different solution, which is a mechanical splice. So let's see what are the advantages of the mechanical splices in terms of transfer of loads. If we compare mechanical splices with the traditional overlap, we see that the traditional overlap, the loads are transferred only by the surrounding concrete. So there is once the concrete, the element is concreted, if there is a problem of a failure of concrete, there might be a problem in the connection of the section. So there are accidents reported where there was not proper, there were not enough stirrups. This is a picture is showing exactly where, I think it's self-explaining. So when there is no concrete, there is no connection in the case of the traditional overlap. When you have mechanical splices, on the other hand, the mechanical splices are designed, and the certifications, the rules that are related to mechanical splices are asking that the splices, once the reinforcing bars are splices, is spliced, it behaves like a continuous reinforcing bar. Couplers are tested in air, so they need to pass the same test that a plain reinforcing bar has to pass. So once the concrete is failing, normally you wouldn't see any problems in the inside structure. So the possibility of having a failure of the structure, inside structure, is very, very rare. So say this, it's obvious that we're not talking about the same thing. Just comparing a mechanical splice to the traditional overlap is different. It's technically different. But we can see more in detail what more advantages can bring the mechanical splices. So first of all, it's a safe solution. So when we just say that the loads are not depending on the surrounding concrete, because it's already it's behaving like a continuous reinforcing bar. Second, it's a certified technology. And when we say certified technology, as I said before, the projects where our mechanical splices are used today are big projects, big concrete structures, and structures where a failure would not be admitted, or it would mean a lot of casualties. So what is important is to use certified mechanical splices. Why? Because the rules are asking that the splice behaves like a continuous bar, and the certification body is checking that. So when a coupler is a certified coupler, you would have a certified splicing, meaning that your splicing is behaving like a continuous bar. Couplers are traceable, meaning that every coupler has a marking, and this is ensuring full traceability, knowing where the couplers come from, when it was. So in case when this was never reported an accident, but even in case of an accident, that it would be very easily to check if there was a problem with mechanical splices. Certification is also meaning quality control. So a certified mechanical coupler needs to come from a company which is having a full quality control program. So the couplers have to be continuously tested, and they are also randomly tested by the certification body. So the certification bodies are auditing more couplers. They make splicing, and that they test them in an independent certification, sorry, in an independent lab. So this means that it's that the splicing system, the certified splicing system, is guaranteeing what the engineer specified. These are some examples or approvals. This is a CARES certificate of approval for couplers. In Dubai, we have DCL also, which is auditing and releasing certificates for splicing systems. So we always invite engineers and consultants before specifying couplers, also besides specifying couplers, also to make sure that the couplers are certified couplers according to local norm or according to one of the norms that are more the most used norms for splicing systems. So because this will be the way to guarantee the safety of the structure. So, and going back to the technical advantages, the splicing system would avoid congestion, so with a better quality of the finished elements. The bonding of surrounding concrete, which is a limit for the traditional overlap, because we saw that it relies only on the bonding of surrounding concrete. In this case, splicing systems are tested in air, and once they are inside the concrete, there is an extra help of the bonding of the surrounding concrete that is also increasing their strength. Design's flexibility, a smaller section can be designed because there is no need to be limited from the amount of steel in the section, and for more saving, because it is using mechanical splices is helping to use over and over the same formworks, because they don't need to be drilled, prepared, or they can be used many times for use and reused. So this was more about technical advantages. Then we see constructive advantages in prefabricating rebar cages, for example, by using when using mechanical splices, it is possible to prepare before rebar cages and assemble on site. So this is one of the most typical reasons why one would use mechanical splices. Climbing formworks, for example, again, it's allowing to use, is the only way to use this kind of formworks is to use mechanical splices for the slab in the second phase. Same D-walls and top-down structures is a typical application of splicing systems. Less splices and longer elements. Obviously, if splices can be used, there is no reduction of the bar. If we think of a 40-millimeter bar, 50 times the diameter is 2 meters. So to have one bar would be 10 meters and not 12 meters. When you use splicing systems, the full length of the bar is used, and there are less splicing in the long elements. If we think a structure going to the vertical structure, it's 5 instead of 6. Precast concrete elements, again, it's the same as prefabricating rebar cages. Also, precast elements can be prefabricated, and obviously on the job site, in an ideal world with only mechanical splices, there wouldn't be rebars protruding on the site. So far, nothing new. This is all the typical advantages and known features of mechanical splices. What we're trying to show today is the potential of mechanical splices in the green department, meaning that there is a need, there is an emergency of that is asking all of us to reduce the CO2 emissions, and to do that, there are when we're talking about the reinforced concrete, there are two possible ways. When we're talking about the steel in the reinforced concrete, either the emissions of the steel coming from the production of steel are reduced, or using less steel whenever possible, obviously respecting the constraint of the structure. So the idea came because we saw that so far there's the mechanical splices have been seen all the time, like prefabricating, all these advantages we just spoke about, but it was never seen as a possible vehicle to reduce the steel amount in the concrete element. And with the steel amount, so less steel means not just less steel, but you would have less trucks of steel on the road, and less loading and unloading energy, and we will see a little bit more. But this is really a first step to understand the potential. So there is a lot that can be done also in investigating more what can be the advantage. But what we started doing is a first approach to a new to understand what can be the potential. And we will see now. This is the core of this STARS project. What the IEA, the International Energy Association, is telling us is that the constructions in the construction sector and the buildings are responsible for nearly the 15% of the CO2 emissions, which is huge. And at the same time, some associations started to give some guidelines to reduce the CO2 emissions from the earliest design stages. So this is what we're trying to inform here, what to help this idea to reduce in the design stages the emissions. This is if we look at the emissions of the embodied carbon in a building, this is coming from ISTRACTI study. The steel is responsible for 19% of the emissions of the embodied carbon in the finished building. So this is the part that we are going to investigate, and we're trying to see what can be the impact of changing to a different system of connection of reinforcing bars. What would be the impact of going to mechanical splices? So first of all, we're trying to understand. We just check the weight of a coupler versus the overlap. Just to have a first idea, the overlap has been considered as 50 times the size of the bar. So these are the weights of the couplers, and the equivalent overlap would be this. So as we can see, the difference between especially for the higher sizes, can be up to almost 1/20 in weight. This is what we are checking today. We're considering the same emissions for steel and for the steel of couplers and steel of reinforcing bars. This could be adjusted, but as I said before, this is the first step. A lot of further investigations can be done. It can be this project will be developed more, and will go into detail in the next months. But as a first result, we are going now to check an existing project that the BARTEC company did in the last few years. It's Grand Paris, which is a railway project where a lot of for the expansion for expanding the railway around Paris, where there were a lot of mechanical splices specified, but only for a few applications, so not to every single splice. So just with a part of reinforcing that was designed to be spliced with couplers, we delivered 320,000 couplers only in 2021, between 16 and 40 millimeters. So the first idea is to see, okay, these were 320,000 couplers. What would have been the situation? What would have been the quantity of steel if instead of these couplers we would have the traditional overlap? So how much steel was saved because of these 320,000 couplers? And this is the result. So this is the weight, the breakdown of the weight of the couplers, and this is the breakdown of the weight of the equivalent reinforcing bars that would have been if this traditional overlap was used. So this is breakdown. Let's say it all together. All together is the total steel that has not been used is almost 3,000 tons. The total steel of couplers was only 173 tons, which means 2,600 tons less of steel only for this part of the project where couplers were specified. This can be converted into tons of CO2 that were saved, that were not put in the air. But this is not just about splicing systems, because and the steel, because it's obvious that the steel bars have to be put on trucks to be transported to the job site, from the factory to the steel fabricator, from the steel fabricator to the site. So if we see the trucks of couplers that were used to put these 320,000 couplers, only 8 trucks can carry this, and this would be the trucks for the equivalent reinforcing bars that were not used. So 8 trucks against 108 trucks of bars. So this is making quite a difference, especially in a jammed traffic network like the one around Paris. Emissions of trucks, everything can be added in the calculation, and obviously is more or less 8% of what would have been. So this is already giving some first conclusions that mechanical splices are certainly a green solution compared to overlap because of the steel saving. But only few projects are using couplers and splicing systems for a limited amount of applications. We don't see splicing systems in every single project, but only in a few cases. It is, as a matter of fact, because today we can say through also the certification bodies that the spliced bar with the coupler is behaving like a continuous bar, technically it is superior to the traditional overlap. So the certifications are telling this, but on the other hand, there is this idea that mechanical splices are considered an expensive solution. So in many cases, the use of mechanical splices is limited because of this idea. We will come back later onto this part of the cost, because this is not completely true. So based on this, we saw this case study on a project that was made where only one part of the design, only one smaller part of the project was designed with couplers. So we had the idea to go a little further and to understand, what if we put splices everywhere, mechanical splices everywhere in a project? What would be the result? What is the real potential of this in terms of reduction of steel? So this was quite a challenge, because we don't know how many. It's not easy to say how many splices we have in a building. It's certainly can be calculated, but it's not in the. We don't have a breakdown for every building of how many overlap, how many connections were done in the bars. So all this depends on the code. This depends on the type of section and type of structure, on the element, and all this. So it's the design also is changing until the last day. Is not always clear if something can always change. So we needed to understand and try to make a model and simulation to find out how many couplers can be, how many splicing in general are in the structure. To do that, the part of the bigger parts was quite easier, because there are projects where all the splices 32 and 40 millimeters are done by mechanical splices. And by analyzing these projects, it was possible to find out that average, there is one splice every 6 meters of bar. So this is the first finding that we had, because for projects where we knew that all splices were done with mechanical splices. So very easy. Obviously, the weight of the steel of the rebars divided by the number of couplers comes out the length of the weight and the length of how many splices per meter. 1625 millimeter splices more complicated, because we didn't have records of projects where all 1620, 25 millimeter bars were spliced with mechanical splices. So we had the idea to check the logs of the software for the cut and bend machine. So this was we used the logs from Ariadis. Ariadis is making software for cut and bend from steel fabricators for cut and bend machines, and we did not consider rebars smaller than 16 millimeters, because it was very difficult to give sense. There are stirrups, so 16 millimeters was the minimum size that was considered. There are we consider several projects. The stats based on the loss of several projects, so it was not one project that was considered, it was many projects, and they were all put together, and to try to understand if there was some kind of rule and find this breakdown per size. So we saw the cuts that the machines are doing for each project. And we had this breakdown, and we could cluster in four size. We assumed that only 90% of reinforcing bars are spliced, and by doing this, we assumed 0 and small bars are waste. So no overlap, no splicing for these bars. 2 5 meters, 1 every 4 meters, 5 7, 1 every 6 meters. Then all this has been weighted on the global on the weight breakdown. But to cut a long story short, we came to the same figure. That was quite surprisingly. We had the same 1 splice every 6 meters of bar. So we once we had this result, we could start from the breakdown of the weight for projects and to see to convert this weight into an amount of the splicing in the structure. So when we add this information, we can basically take any project where we know the amount of steel that is foreseen for the project, forecasted for the project. And for example, this is a 18-story building, about 2,000 tons. And by using this rule of 1 splice every 6 meters, divided obviously in the different sizes of the rebars, we had more or less 95,000 mechanical splices, and if we compare this to the equivalent overlap, it gives a 20% steel saving. Two Towers Bridge, about 4,000 tons. This is giving about 140,000 mechanical splices, and when we compare to the equivalent overlapped bars, we have a saving of 24%. Again, this is the case that we imagine when we imagine that the full amount of splicing, instead of doing it with the overlap, we do it with mechanical splices from 16 to 40 millimeters. We don't consider less than 16 millimeters. We tried to go a little further because I had an objection at some point. We say, yeah, but we're already using mechanical splices in Dubai. There's so much used, so no need to increase or what. Okay, let's see what was exactly the saving and what is the potential saving. So this is a project in Dubai, Bloom Towers. We made, as it was made, 64,000 couplers were used. So in this case, 6% only saving. If 100% of splicing was done by mechanical splices, there would be more than 400,000 mechanical splices, and this would bring a saving of, would have brought saving of 18%. Only 6 against 8. Okay, splicing was used, but 6% only saving of steel compared to the potential of 18%. So another project is called Al Kamal. In this case, 30,000 splices that were used, 4%. The potential was more, almost 400,000 mechanical splices that would have brought a reduction of steel of 20%. We have the Deira waterfront development, few couplers only used, about 5,000, 1% of the saving. If all was done with mechanical splices, there would have been 18% saving. So this is telling us that yes, we save something with mechanical splices, but a lot more can be done. So conclusions are that this is a very, very interesting conclusion, is that this is a known and certified technology. So we're not talking about an idea of a new product that can bring a solution. This is a product that's already existing since 50 years. So it's a known and certified technology that is bringing more safety, that is bringing all the technical benefits that we saw before, constructive benefits that we saw before. And obviously there is a straight equation that the more mechanical splices are specified and used, the more steel is saved, and so less embedded carbon and emission. Obviously, we have to check the cost at this point, because this is the first objection is, yeah, well, okay, this is all nice and perfect, but how much is costing this? Again, we go back and try to compare overlap to mechanical splices. Let's go straight to the point. This was done in end of March, so there might be some variations at this time, but it's a comparison between the market cost of the mechanical splices against the just the overlap bar. So we have to consider maybe the 50 times overlap bar. It's the cost only of the steel, so we're not considering anything else. And just by seeing this, we see that after 25 millimeters, the cost is more or less the same. 32 and 40, it's much more. It's much less expensive to use mechanical splices against the overlap. 25 is more or less the same. Less than 25, the overlap is less expensive than mechanical splice. Then, obviously, the more the project is as a weight is important, because is a more massive structure, bigger sizes. So this will compensate the small size. So every project is different. We're going to in a minute we'll see some examples of that. But before that, as I showed here, is a finished mechanical splice versus the only the bar. But let's see what the overlap. It's not just about the bar that should be considered, because the overlap is also fixed. Some steel rod is used to tie the rebars together. There are in the area of the overlap some extra stirrups. The codes are asking to increase the stirrups, the amount of stirrups in the overlapped area. So there is some extra steel there. The material cost could be higher if there is more than 50%, sorry, more than 50 diameters. So we always assume 50 diameters, but there are many cases where it could be a longer overlap distance. So more overlaps, you have more rebars, so you have more trucks, more loading and unloading. These are costs, because the cost of moving trucks, the cost to load and unload the material, the energy and everything. So, and also at the end, the overlap is not even a certified splicing. So it's a two rebars just joined together with a steel rod. There's no certification. There is an uncertainty due also to the lack of certification. There are also some hidden costs that when overlap is used, like formworks preparation. So the formworks have to be drilled, have to be prepared for the rebars. Congested areas, the placing the steel is difficult. In the same congested areas, there are longer operations to pour and to cast the concrete and to verify that is correctly casted. So mechanical splices are always allowing to build more quickly. So it's not just about it can be really help also in saving time for construction. And the cost of the steel may change, may become higher during the project execution. For example, in the case the breakdown we saw before would change. So the price, all this is telling us that the price for the end user of the overlap is variable. So yes, it is the cost of the bar, but it's that plus, and we don't know. We should check what the plus is to make sure to have a correct comparison. Why that? Because mechanical splice is just the cost of the rebar preparation plus the cost of the sleeve, and it's a fixed price because it's just the cost of the two threads plus the sleeve. If there is a change in the steel during construction, this change doesn't have a big impact on the cost of the sleeve, so it's not having the same variability during the project execution. So we can say that the price for the user something fixed that we know how much it costs against something variable, which is depending on a lot of other possible factors. We go back into this project that we saw before just to understand the impact on cost, because we know that we know the cost, we know how many, and we know let's see what is the increase in case of this first project. If this was done all with mechanical splices, the cost increase would have been 0.5%. So, and in this we saw that the using mechanical splices was saving 18% steel and CO2. I'll work them all. Same exercise, cost increase 0.7% if this was done only with mechanical splice, all completely with mechanical splice. And here we would have saved 20% of steel. Dairy water from development, 0.4% of cost increase, still CO2 saving 18%. So this is telling us that specifying all mechanical splices may have an impact only of less than 0.7%. This cost increase is not, I mean, is again something only the reinforcing bar, and is not considering all the variables, and also the fact that all splices might be used. This would generate a very large volume of mechanical splices, and obviously the market price of mechanical splices would go down. So it is reasonable to think that this extra cost could be reduced because of the larger amount of mechanical splices to be installed in the market and to be put in the market. This is a basic market rule of a high demand. So the impact on the environment is always higher than 18%. So this is another fact. And when we go back to this breakdown that we saw before, where the steel is responsible for 19% of the embedded carbon, this means that there is at least a 3% of reduction of the embedded carbon if only splicing systems are used. So this is huge, and also something that has to be said is it's there. It's not something that we imagine. It's not a new product. It's not something. It's something that is already existing, and that is certified, and that we know already very well. So if we also again we go back to what the International Energy Association was telling us about the large responsibility of the construction sector for the emissions, we can say that by specifying mechanical splices and specifying certified mechanical splices, something towards the emergency can be done right now. So this is the final conclusion that we can that we should think about, because it is something that can be that can help immediately. So this is pretty much. I try to run a little bit, but to be in the time of in the scheduled time of 1 hour. So I hope that everything was clear so far, and yeah.
Yes.
Thank you for the attention for everyone who was there today.
Yes. Thank you very much, Alessandro. A very, very interesting topic, and some very interesting studies that you've done there. So just a reminder to everyone online, if you have any questions, just please type them into the chat box, and we'll ask Alessandro. Just while we're waiting for any questions to come in, I thought it was a interesting observation about the fact that for long structures, you end up with, if you use mechanical splices, you end up with less number of splices because you're using the full 12 meters of the rebar instead of the effective 10 meters if you've done the lap. So your traditional lapping, you may have 6 splices, but with mechanical that would be reduced to 5. Also, the potential savings here, potential increase in quality of construction, especially where there's reinforcement congestion at the beam and column connections, which is always an issue when you do site inspections. So yes, so thank you. I think we don't have any questions coming in, Alessandro. I think the only other observation I have is the potential savings of carbon, CO2 embodied carbon of up to 20% for a small increase in the cost, and the fact that as more and more couplers get manufactured, the cost can come down. So maybe in a few years it'll be it could be standard practice for the bigger rebar connections. Okay. Thank you very, very much, Alessandro, and I'm sure we'll talk to you again in the near future. So